Hello, today you should have just finished up doing the gizmo on the different types of waves and their characteristics. We're going to summarize in a few notes. I made a Google document with the fill in the blank notes that you can open. If you'd rather take them in your own note paper and not use the fill in the blank template, you can do so. Just then take a picture and upload it on top of the document or upload that for your assignment submission. So we want to be able to distinguish between transverse and longitudinal waves and then identify the different characteristics of each. Don't worry about the agenda on the right-hand side. I should have deleted that from last year. So defining a wave, first of all, a wave is an oscillation or vibration in matter that transfers energy. It can also be a vibration in a field. Next unit, we will talk about light, which is electromagnetic radiation, and that can transfer through fields. So it doesn't need a medium to travel through. It just transfers in electric and magnetic fields. And the medium is the material through which a wave travels. So a water wave is traveling through water, that's the medium. Waves on a slinky travel on a slinky, the slinky is the medium. Sound waves can travel through air, so then air is the medium. There are two types of waves. We can classify waves as being either transverse or longitudinal. In a transverse wave, the medium vibrates perpendicular to the direction that the energy travels. So in this particular picture on the bottom, they're moving their hand up and down, and the energy is traveling to the right. And so those two are perpendicular or at right angles to each other. That's a transverse wave. You can also take a slinky and move it back and forth, your hand back and forth, and this creates areas where the slinky coils get pressed together and areas where they're stretched out. That's a longitudinal wave. So the individual coils on the slinky are moving left and right. The energy is moving to the right. They are parallel to each other. So that is a longitudinal wave. In a transverse wave on the left-hand side of the notes, there are different characteristics. Some of these will also be characteristics of a longitudinal wave, but the first two, crest and trough, are characteristics that only apply to transverse wave. A crest is the high point in a wave. The trough is the low point in a wave. By the way, I am going kind of fast here, so you can always pause the video as you need to catch up. That way you can kind of go at your own pace. So the crest is the high point, the trough is the low point. You would also have a crest right here, a crest right there, and you'd have a trough there and there. Another term we need to understand is amplitude. Before we can define amplitude, we need to know what the equilibrium position is. The equilibrium position is where the medium would be if there was no wave. So with water waves, the equilibrium position would be where the water surface is on a calm day. If you were making slinky waves, the equilibrium position would be where the slinky would be if you weren't creating waves. So this black line right here represents the equilibrium position on this picture. And the amplitude is the maximum distance from the equilibrium position. So we measure the amplitude from the equilibrium position up to a crest or the equilibrium position down to a trough. A common misconception or a common thing kids will do incorrectly is to measure the amplitude from the crest to the trough. That is not correct. The correct way to do it is from the equilibrium position to the trough or the equilibrium position to the crest. So it would be half the distance from crest to trough. And then the final term for transverse waves is wavelength. The wavelength symbol is this right here. It's a Greek letter, it's lambda, and that tells us the length of one complete wave cycle. So a complete wave cycle, you need to have the up motion and the down motion. So that red line I just outlined is a complete cycle. It's one complete up, one complete down. You can also measure the wavelength from one crest to one crest. So two neighboring crests or from two neighboring troughs like this. And if you look at all three of those lengths, they all are about the same. So it doesn't matter where you measure it from. Sometimes it's easier just to go from crest to crest or trough to trough. Sometimes it's easier to get it from the beginning of the up part and then the end of the down part. So whatever makes the most sense for your particular scenario. Sometimes you won't be able to directly measure the distance from crest to crest, or it'd be very difficult to do so. So in that case, what you do is you take the total distance included in all of the wave. So if that total distance here is 10 meters. You count the number of wave cycles in that distance. So if we counted these wave cycles, we have one wave cycle there, a second wave cycle, a third wave cycle, a fourth wave cycle, your fifth wave cycle, and then you have a half of a wave right here. So then to get the total wavelength, you take the total distance, the 10 meters, divide it by the 1, 2, 3, 4, 5, and 1/2 of a wave. So 5.5 waves to get a wavelength of 1.81 meters. Now moving on to longitudinal waves on the right-hand side of your notes. A longitudinal wave doesn't have crests and troughs. It has compressions and rarefactions. The compressions are where the particles of the medium get compressed together. So we have a compression here, a compression there, a compression there, and a compression there. Those are the regions where they're close together. And then the rarefactions are the regions where they're stretched out. So we have one there, one there, one there, and one there. So a compression would be similar to the crest, perhaps, the rarefaction, similar to a trough, but they're not exactly the same thing. We still have a wavelength in a longitudinal wave. It's a little bit more difficult to measure directly because there isn't necessarily this really high peak, but we measure the length as one complete cycle again. So here we can measure it from rarefaction to crest to crest. So we can measure the wavelength there, or you could also do it from rarefaction to rarefaction. So we could measure a wavelength right there. Either one would work. And that is it for the notes. So or submit your copy of your notes or an image of your notes if you took it on paper, and then have a great day.